What I'm showing you here is a famous so-called visual illusion. Probably some of you have seen it. If you've never seen it before, you may not notice that there is a Dalmatian dog in all these patterns of spots. Now, if we go back to the original image now, what's interesting is, from a human computer vision point of view, is once you've seen this artifact and you've identified it with the Dalmatian dog, you may not see the image for years, but as soon as you will see it again, it will pop out and you will see the dog automatically. So somehow you've captured this so-called illusion. It's called an illusion because as you traverse where you see some legs, for example, there's actually no lines there, there's no change of contrast, but once you've decided that there is something there, you see typically something that's whiter than a background, but there's no difference. And there are many, many such famous illusions. And so the area I initially studied in can come under the word of perception, and we try to propose models that would explain this behavior of our visual system. And you have similar studies in the area of hearing, listening to music, etc., where you also have illusions, and it's clear that the human brain is doing interesting, creative things with our sensors and the data that bombards us all the time. Things that are not all that obvious to understand. And over the years I've come to feel that by interacting more and more with the art and artists, I potentially would get some interesting viewpoint in this problem of perception. And the reason for that is that there are good examples of famous artists who've actually laid out for us their thinking process. So this can give us a starting point to try to understand what kind of representation are explored as we represent here, for example, a cow or bull, in the case of Picasso. And of course, artists I consider them as a class of experts in perception. So they may not have the same scientific background as, let's say, people in psychology who study visual perception as well. But they have to think hard and explore how do we, in the case of vision, see the world, and how can we then reinterpret it and play on these so-called illusions. For example, this is one way an artist might try to propose to you something that will surprise you. So here's an example of an artist from Spain, Pablo Gargalo, who obviously makes a good use of these illusory contours. So for example, here there's absolutely no contour there, but we do see something like a face, and we are happy to imagine that there is a contour. Here's another artist, Bridget Riley, who's linked to Goldsmith, where I come from, and she too has been playing with other types of visual patterns that create illusions here of depth, and sometimes these illusory patterns, not these ones, will actually induce motion, although the pattern itself is static. So this is more background and motivation for where I come from. So it's a mixture of understanding of vision using computing, and starting to interact with people in architecture and the arts over the years. And interestingly, nowadays with computing, we have good enough machines and good enough ways to program them that we can start interacting with artists and put at their disposal some of these models that before were only understandable or used by people in the science. So here's an early example. Ed Burton, someone actually I'm involved now in London in creating a follow-up to this project. So in the early 90s and mid-90s, Ed was a so-called artist programmer. So he already was bridging the gap between those two fields, and he explored a particular model in computer vision that had been proposed maybe 15 years before by David Ma in MIT, which is this sort of blocky model you see in the middle. So this is called a generalized cylinder type of representation. And he became interested in this type of model that had been proposed by people in computer vision as a potential representation of shapes, of 3D shapes. And he started to explore that in his system, which he called ROSE, representation of spatial experience, in exploring how potentially this model would explain how children learn to draw. So what you see then on the both sides, on the left and on the right, are example. One is a drawing by a child, here about 5-year-old, and the other one is produced by his simulator of the type of representation that potentially are used by the human brain as they're learning. So this kind of work inspired the first work that I'm involved in that I want to present today. Today I will try, if time permits, to go through 3 pieces of work, 3 different type of work. This is the first one, and it's directly inspired by the work by Ed Burton. This is work with an artist called Patrick Tresset. He was a painter and then started to develop rapid sketch technique of representing especially faces. And he had, before that, studied computing, and so he had learned some programming. This was back in the 80s, I believe, a while back. And he was stuck in his art practice, and he decided that he wanted to go back and explore programming again. So we met about late 2004, and this project came out of this initial conversation. So essentially what we're trying to do here is we're trying to understand what I call the grammar here of the artist, the set of processes that potentially are put in place when the artist, in this case of face sketching, looks at you or looks at an image of a face and decides what to do next from the blank page. So the first result of this work was called an icon for the artistic automated iconograph. Now we call it Icon 1, so we're in the second generation. I'll tell you a little more about that in a few minutes. And that first system was purely a software-based simulator, and it had broken down in a few set of processes what potentially the artist is doing with the image of a face. So here's an example of the rapid type of sketching that Patrick does. So actually different potential outputs. There's a number of there's a flexibility in the style, in the speed you use, in what you do with the lines once you've started to draw them. So each drawing of even of the same person might actually look different. So you can imagine, and later we will try to model that with our system. I'll say a little more about the motivation in a few seconds, and of course if you have questions at the end, please. So this is what the system looked like in a simple summary here, a sequence of steps. The first step was simply to find faces in images, which is, so back in 2005 it was more or less difficult to do, but it was becoming current. Nowadays you would say from an algorithmic point of view it's easy to do most of the time. So the first step obviously is to find what the object of attention. And then there's a number of steps which are linked to the method of Patrick himself. So in discussion with him, he would tell me what kind of features in an image are driving his attention, and then how he used these regions to then decide how he's going to control his arm and start drawing lines and then do these rapid gestures along these gesture curve. So what you see here is an example of a set of so-called gesture curve which have been processed from special regions of the image. Again, each of these steps would be informed by what the artist thinks they're doing in their mind, and in the conversation with someone like me we decide, well, what kind of method we know about that we could do something alike what you're describing as the artist. So this is in the conversation we come up with then a simulator, and one of the motivation of this work is to basically with this simulator help us understand what is going on in the mind of the human. This is really the original goal, at least from my viewpoint. From the viewpoint of the artist himself, there are other goals such as exploring variations of their stylistic signature. So this kind of work, in the case of Patrick, actually he tells me encourage him at one point to actually go back to his practice and start modifying his style and then explore other variations. So it can be used back. Also, another motivation might be as a way to explore out of a particular dead end, let's say, for an artist, after a while, explore further on. This is one of the initial, very early type of output that would come out of the system, where we were not controlling too much the gestures. The gestures we were using to fill in selected regions. So you have something which is very nicely curved in terms of an outcome, and you could say, well, this might be linked to a particular style. So this issue of what is a style of an artist who draws or paints is obviously an open issue. It's an area of interest in aesthetics, both on the computational side and the theoretical side. So this is much later. We had explored with different ways of mimicking the rapid gestures. In this case, different ways of using the shaded area we would extract, and this is more or less the final style we reached with the project we call Icon 1, and you have some examples here. This is a commission we did for a new scientist who was doing a piece on Stephen Hawking. So since we've started to propose this work, we've had a number of commission and exhibits, which is something we had not really planned for. The project itself was really casted as exploration, more on the science across art boundary, but it's turning out to have some interest in terms of producing art itself. I'll say more about that for when we reach Icon 2. So the second project, which is the ongoing project in that space, we call Icon 2, bridges the gap with robotics this time. One conclusion we reach in the previous project is that although we were able to produce a system that has dynamics, so here I'm not showing you a video yet, I'll show you one later, and you can sort of maybe get an understanding of what kind of process might be used by a particular artist. We were never getting all that close to the style of that the artist himself would qualify as human. So there's still a lot of regularities in the way we do the hatching here and the high curvature points, which are sort of a signature of a machine, and it's very difficult to get away from that by simply devising software. At least in our case, we found it was very difficult after trying many times. So we went, in the context of the second project, the follow-on project, we decided at one point, this was late 2009 now, I'm talking about, to look at robotics. In the meantime, robotics had started to become much more approachable, similarly to using software to manipulate image, such as Photoshop, processing. I've made it approachable to artists who are not necessarily very advanced programmer or engineers. Robotics is reaching also that stage. It's still a bit hard to get into, but much more approachable. So in late 2009, we decided let's try it. Let's see whether we can actually incorporate that in our work. And the hope was that by having actual robotic limbs, we would get away from the problem of modeling all these let's call them uncertainties that are typical of a human when they draw a line, which is rarely a straight line if they're not trying to draw a straight line. Even when they're trying, even when we're trying, it might be difficult. So we put in place, we refine our system. The system was not software anymore, and therefore, because of the robotics part, we were guided in the sequencing of the steps involved in producing a system that draw. So in particular, we have all the steps of the robotics here, which have an impact in the sequencing of how you lay down those lines on a piece of paper. If you're a purely software, you don't necessarily have a guide to do this. So now the guide is actually we have to move joints, we have to move an arm, and the arm will be with similar joints to a human arm. There are other bits here which we haven't really explored yet. For example, when we talk about experience in the bottom there, how a human artist will rely on what they've learned before or try to mimic the style of another artist is something we set as a future goal in terms of where else this work could go. So this is not achieved yet. And just to give you a feel for how you go about robotics programming, one thing with robotics programming is you have the issue of scheduling, but basically meaning that you have a set of processors and they have to communicate and decide who does what at what time. Fortunately, since about 2009, 2008, there are now very good software platforms that are available and help you do that. So, for example, for those who are inclined, there's something called YARP and there's something called ROS. I would recommend looking into ROS, Robotic Operating System, open and available to everyone. So we were able to achieve incorporating robotics in our simulator thanks to the fact that there's a community out there now that is blossoming and making it available to us. So this is now to give you an idea of the kind of style we're achieving. It's much closer to an actual line drawing, and in a way, since we're in the centennial year of Alan Turing, one may argue that it's passing the Turing test for drawing. If I don't tell you the machine did these drawings, you might think, well, it might well be a human. We may argue about that, of course, later on. So this is what the robotic platform looks like. So when I say robot, robot can be many things. Here the robot is really just an arm. It's pinned to a table. It has a few joints like your arm has. It also has a camera on a stick, and the camera has some degree of freedom, so it's able to rotate. It has two degree of rotation of freedom. So the camera, the eye is always, when we initiate the system, it will start looking around, trying to find a face. Usually, if someone is standing there, it will find your face. Sometimes, if there's nobody, it might find something that looks like a face on a wall, etc., and start drawing that. At that point, we've had some technical issues, so I will, hopefully you'll excuse me, I'll just be switching between presentation and videos a few times now. Okay, this is a later video, sorry. Right, this one. So I'll let the video run. This was presented at ISEA in Istanbul last summer, this particular version. So the drawing takes about 10 to 20 minutes. It depends on the environment. By that I mean the lighting, for example, the background on the walls. It depends also on you. The sitter, whether you have lots of hair, for example, will have an impact. So here we're speeding up, obviously. One of the comments we get when this is active, we call it Paul the Robot, is that the process of watching the robot being active is very interesting, and people typically feel empathy for the robot arm. So not just the drawing itself, but the actual motions and the I didn't put sound here, but the noise, the squeaking noise that the joints make. So we found that robotics not only allows us to maybe in a way bypass the problem of representing uncertainties in drawing as a human does, but also allows us to engage with the public in a different way. Right, so what next in that direction? So the focus of our work at the moment, currently, and in the next, I would say, couple of years probably, is the issue of feedback. We've started by feedback. There's different type of feedback we may consider, but the most obvious one in the context of understanding how a human creates a drawing is issues of vision and touch. So I emphasize those here. So in particular with the camera system, we have the camera now looking at the drawing and the arm as it's working, and we're trying to again, in discussion with the artist and myself and other people involved in the project in the periphery, people in robotics for example, we're trying to come up with schemes to put feedback so that the robot will, the system would be influenced by what they draw, which is the case of a human unless you go about doing a piece very rapidly or blindfolded. So typically you are interacting with the piece, it's influencing what you do next. So that's our main challenge for the time being. Another area I think of interest in general to anyone who's interested in this kind of work is to explore the issue of interaction. So I briefly mentioned how the public feels empathy for these systems, but there's also the issue of collaboration that could be explored. So this could be collaboration between robots, but eventually I would like to take this kind of work in the direction of collaboration in artistic practice between humans and robots directly. The potential there probably early on is more at the level of children engaging in playful drawing activities than the professional. At least that's our feeling at the moment. So this was the first main project I wanted to propose to you today. We could go in more details, and I'll be happy to discuss this work later if you want. And I want to now go to another area of work I'm involved in, which is the area of computer games. How I make the link between the three projects I'm presenting today is the issue of art. So in all the cases, the work is revolving around the world of art. So in computer games, you may probably know or understand that the art practice is one of the key components of producing games. So essentially, any new game that comes out today, computer game, has to have a different artistic signature to it. Even in a series, let's say Grand Theft Auto 21, it will have to look different from 20. Otherwise, it will look the customer won't appreciate. So in a computer game, if you look at a team that makes the games, the artists represent probably, usually, at least a third of the number of people involved in producing a game, if not more, if not even half. So they're definitely a key component. What we're doing here, in the context of the project I will discuss now, is we're exploring with artists and so-called games designers, the people who think about playing the game, how to design tools that would allow them to do either more efficiently producing the art they're producing, or potentially having new effects interesting effects in the assets they create. So where computer games stands today, they stand at a quality which is reaching movie quality. And in fact, the area of games now is recognized being as important worldwide as film. So these two worlds are definitely, the gap between them has shrunk. Games used to be looked upon as very poor on the art side compared to what's done in terms of digital effects in films. This is much less the case today, and you can imagine that within a few years the quality will be on par, at least on par. The main difference will be interactions. So the project I will now describe somewhat briefly, is, we called it ProGen. So it's the genesis of artistic content in the context of games, and the pro in the front stands not for professional but for procedural. So essentially we're designing tools that will create methods that rule on the spot, real time. One of the main reasons for going that way is that typically an artist and a designer, they would like to have tools that allow them to modify something they've created on the spot, potentially trash some of it and recreate a new piece to fill the gap. To be able to give them those tools, those kinds of tools, we have to go into the area of computer graphics called procedural modeling. So this is a snapshot of where the technology stands at the moment. So what you see is the technology is very specialized. It only targets cities and architecture for the moment, but you can imagine that these kinds of ideas could be extended to other types of objects and environments. A lot of what is, in terms of the tool, the platform that we've created is given to the artist and designer, is provided at relatively low resolution, or rather low texture resolution or low quality in terms of the graphical output. And the reason is that allows us, for the time being, with the technology we have, to provide all this interactivity to the artist in real time. So what you see from the top left to the bottom right is sometimes called white boxing. So basically we're giving the potential to create a lot of geometry that will be incorporated potentially in a game level, but it may be left completely white or gray here, the bottom right, or have very rough materials identified so that you can already start to specify the type of material you will use. But then eventually this is exported, once the designer or artist is satisfied, is exported to a game engine, which is the kind of result you see on the bottom left, and we'll see more examples of that later. So now I'll show you a few videos which illustrate the set of tools we've started to produce for them. If I can get to my movies. Well, so this is something we call Map Creator. It's been designed by a partner in the team from UCL. And what it allows you really is to mix different styles of road networks in this case. So you see at the top you have three types of road networks, something on the left like Manhattan maybe, and other road types that are more complex. And the method is able to mix these different styles. Potentially the styles may have been designed by hand by an artist as well, in a way so that there's a natural transition between the three styles. In this case, three. We limited ourselves to three just to demonstrate the idea. So this is an example of the type of work that today laying out road networks is something which may come from, for example, inputting a real city network, which has its own problems in terms of what you do with all the information associated to it, so that it's useful for in a games engine. Or you may design it by hand in 3D Studio Max, for example. So that's one of the reasons this particular tool, very specialized, is provided here. Then we have a set of tools which is purely interactive, and essentially it's again a drawing tool. So there's a link with the previous study. But what you're drawing now is city blocks, roads. It will take care for you of dealing with all the issues of topology and geometric problems. So we will find the right junctions for you, and at any time you can actually go at a particular location and modify it. So in everything we've designed, it's been designed informed by the artist. They always want to have full control. If you provide them with something automatic like the previous video, at one point they want to have the control to start modifying things. So you always have to keep that in mind. The human wants to keep the control, even if we know how to do it automatically. I'll skip some of the videos, sorry. So now you have the two tools we've seen before combined in one. So essentially now we've removed control from the human for the time being, and we're generating a city by using the map creator. So the map creator is mixing again these different styles, potentially designed by the artist as an input, and is building a city by mixing these different stylistic signature of cityscape. And it's doing it in 3D, and not only the roads are parameterized, so you can modify them, but the buildings as well. So maybe, so I have what, 20 more minutes? Just checking. Yeah, okay, just pacing myself, thanks. Right, so I just want to give you a feel here for what I'm saying about the buildings as well are parameterized. So you can have sort of boring classical ways of modifying features, but we also have ways of modifying these buildings by gestures. So you can actually go over a building and mimic one building, one style of a building across an entire road, for example. So today this is something you have to more or less do by hand using again something like Maya or 3D Studio Max. Here we're trying to provide a way to make this more efficient, but still giving back to the artist. If they want to modify something, a window in that building at one point, they're allowed to, they have the capacity to do that. And we can discuss later what kind of technical issues are involved in providing that capacity. Yeah, so finally, when you have created your set, you can then bring that back in the, let's say, a typical game engine. So this is brought back here in the game engine by a company called Rebellion in Oxford, which is a company we've been involved in designing these tools. So all these buildings and roads have been created with the tools you saw before. Roughly, for this particular piece, the artist that took our tool and used it between 3D Studio Max, the tool, and their engine. 3D Studio Max, maybe I skipped that a bit briefly, was used to create components. So, for example, to draw a particular style of a window. And we use that as a component to populate our buildings. So the entire city district here was created in about 6 hours of work. And Rebellion tells us that typically this takes a week in their current chain. So it's been a success in terms of the initial goal of trying to demonstrate that these tools might provide the artists with efficiency, and then allow them to spend more time on details and refining where they need to, rather than create lots of data to populate an entire city. So there's a lot of things here that are added. Obviously the cars, etc., come from a database in the engine of the company Rebellion. They were not part of the tools we provided. Again, our tools were only meant to produce architecture, like artifacts. Right. So that was the game-like project, and I want to end with a third project which is also ongoing, but has been running for a few more years than the ProGen, the previous one. And again, the reason why I'm showing you that is that it is impacted by artists, as you will see. The domain here is more science or scientific visualization, and it's a collaboration between us and at Goldsmith and people at Imperial College who are experts in what's called bioinformatics and structural proteomics. Sorry, basically they're dealing with proteins. They're looking at genetic codes, and from that they're trying to infer, for example, the shape of a protein, how it will fold in space, which is an open issue and probably the most important problem in that area of science. So we've called the project Fold Synth. Fold refers obviously to the folding problem of proteins, and synth is for synthetics, and this is where we start bringing the artist in the loop. So let's go into some details. So I've mentioned that this is all about proteins. Now there's a link with what we've seen before, and the team working at Goldsmith is the same, more or less the same team that worked on ProGen. That is the technology, the graphical technology put in place comes from the game type of technology. So the idea here is to provide visualization, which traditionally in computational chemistry are more or less static, to provide them with graphics which is interactive, potentially provide them also some playful, more artistic visualization of the data that they might find useful. One of the innovation we brought in this area is that we combine a traditional 3D visualization of strings of molecular structure with a 2D map. So this is the triangle you see at the bottom of the screen here. So this is extracted from what we call a matrix of distances. It's actually giving you information. The color there gives you information about a particular position along the strand, the molecular strand, and another position somewhere else along the strand. So for example, the tip of the matrix here gives you information about the two tips of the strand, how far they are. And positions along the diagonal are sequential positions along the strand. So anything that happens away from the diagonal is representing distances further and further away by pairs. You'll see in a few seconds why this is useful. This is useful actually in a number of ways. So one of the ways it's useful is you can, rather than interact in the 3D world, and anybody who has tried to create data, to create sculptures in the 3D will know that it's very difficult, even if you add stereo, which might actually confuse you or give you a headache. Here you have another mode, which is the 2D mode. So any action that is taken in 3D is reflected on the 2D map, and vice versa. Any action that we take in 2D, once you've understand the mechanism and how it may relate to 3D structure, you can effect directly in the 2D. In particular, we can do, again, drawing gestures or painting gestures in the 2D map. So there are two main types of gestures that are worth pointing out. So these gestures, the horizontal one near the main diagonal, is a gesture that will allow you to enforce constraints that generate what's called alpha ellipses, essentially ellipses in space. So basically you're telling positions along the strand which are nearby, but not exactly next to each other, to stay close to each other. And that by default, this will create an helix-like structure in 3D space. And the gesture which are vertical and away from the main diagonal, these ones have the effect of creating parallel strands in 3D. So they bring long sequence of the molecular strand to stay more or less parallel, and this is what you see here. So this gives you one mode of interaction and creating these sophisticated structure. Now you can see that. Few minutes. Thanks. You can see here that as the molecular structure become more and more complex, it's going to be very difficult to go in the 3D world and try to get a sense of proximity and what kind of substructure is relating to another. While in the 2D map, once you understand how it works, how the patterns that you see here can map to a particular structure, in 2D it's always laid flat for you. So in the 2D view, you always see what's happening in the middle, which you may not see when you're outside, or you can go inside, but then you don't see the outside. So it's always tricky in 3D. Right, I mentioned Imperial. There's one person who's moved to UCL in the team. So we provide classical computational chemistry visualization, of course. The work is meant to be used by people in biology at this point, this particular piece of work. We do introduce some what we think are interesting visualization. You saw here briefly, I'll come back to it, a sort of memory of deformation in space, which we've introduced to the biologists. And now we're going to see a little more of the interaction with the 2D matrix. So you might want to see the colors as a topography. Yes, as we navigate in 3D, we see the positioning on the 2D map. Now here we're removing, we visualize the set of forces that were applied. We remove them so we can unfold the structure in a natural setting. You see some vibrations, so we're simulating bombarding with water molecules. So we're doing things so that it relates to what happens in vivo. And now we're reintroducing the forces for this particular folding at a constant pace, and so this gives you a tool now, interactive tool, to gives you a flavor for that kind of tool that allows you to study folding itself, the process of folding. Here we're doing a similar thing, but for a different visualization, a metaball visualization, which gives you a more volumetric space of what the molecule occupies. Yet another way of interacting with the system. We're revealing the position starting from one corner of the matrix. So this allows you to walk step by step along the strand. That's a natural way of visualizing the forces with this tool. And now we're going in the more creative side. So of course, up to now I've shown you actual simulations of real proteins. But we can use the tool now from scratch and create our own virtual proteins, and they don't have to be proteins at all. So they can be essentially, you can think of them as dynamic molecular sculpture, let's say. And you can, again, you can interact either in the 3D, if that's useful to you, or in 2D. We find that when we create these from scratch, the 2D drawing map is the most used and most useful. So here we're controlling different subregions, and then eventually doing things like copy-paste of constraints. You can think of these as constraints. You can remove them, add them. So these are called unreal here with respect to biology. Essentially, in the distance map that we observe in biology, we tend not to see these constraints which are along diagonals or other orientations than verticals and horizontals on the distance map. Yeah, finally this is the latest piece of work. Now we're looking at multi-objects or multi-proteins and looking at the problem of fitting them together. But I won't go into details with that. Time is running out also. Right, let's go here. So, although this project started now in this current form about 3 years ago. In the last year or so, our team at Goldsmith, we started to use that technology in other ways. So we, as you saw in the movie here, at the end we were starting to do things that are obviously beyond the scope of biology. And we've applied lately the same tool, this time for the visualization of social nets. So essentially behind this is purely playful now. I'm just showing you that. It's not very serious, but it's just to show that the same tools that are developed, in this case for scientific application, can then be pushed back in something which is, let's say, visualizing your social network in a dynamic, interactive way. And here are these memory maps I was mentioning before. So these essentially are tracing the unfolding of objects in space, and they can create quite interesting, sophisticated forms. We haven't found a practical application of that yet, because the initial idea was that the memory visually would be potentially of interest as the form unfolds. But in terms of aesthetics, there is something of interest here, so I wanted to show you that. So that's more or less what I wanted to show you. I just want to conclude with trying just to summarize the 3 projects and how they may relate to each other. So the icon, the one on the drawing and eventually the robot, is really a study of art and artists in the context of understanding the mind of an artist, let's say. In our case, it's mostly about visual perception. I didn't mention touch, haptics, but we don't have that in our project yet, and we need to collaborate with someone who's an expert in that area. But that would be a natural follow-up. ProGen is working with artists this time to create tools for them to use. So the artist is not necessarily in the loop creating the software, which was the case of Icon, or is the case of Icon, the software and the robots in that case. Here the artist is giving us needs, telling us how they work, so we have to adapt to how they work, fit our tools in their chain, and try to address their needs. And finally, FoldSynth is an artistic practice developed in the context of computer games, which was retrofitted into biology or scientific visualization, sorry. And then at the end, as you see, we're starting to get inspired by that work too, and it's coming back to the art side. Thank you very much, but sorry, I thought I had put a few more slides here, which are my credits. I don't want to avoid those, but somehow they return blank. So on Icon, again, the main collaborator is artist, programmer, I would say now roboticist Patrick Tresset, who moved from Paris to London many years ago. On ProGen, you have the core team at Goldsmith I'm involved in, which includes William Latham, a well-known artist, pioneer of evolutionary art. Stephen Todd, who's an ex-IBM researcher and a close collaborator of William. His son, Peter Todd, who I took on a master's, where the first version of FoldSynth, the other project, was developed. And it's a collaboration with UCL, Professor Anthony Steed, who's the head of the Virtual Environment Lab, Dr. Kizzy Yu from China. And at Rebellion, we've been working mainly with people on the design art side, Kevin and James Mars. FoldSynth has the same core team on Goldsmith side, and then the main partner at Imperial are Professor Michael Sternberg, who's the head of the group there, Dr. Lawrence Kelly, who's a postdoc, and Benjamin Jeffries, who now has moved to UCL. Thank you very much.